Oh yeah, we did the mole fraction. The mole fraction is a legitimate question for the test. I think from doing the tests that I have, it might not come up on any one test because it's not considered that big a deal, but it could. Which we say a lot about a lot of concepts. I know there are a lot of things that could come up, at least in minor ways. But then again, they might not. So the mole fraction is the ratio that this is of the total. So what you want to take is part over total, which is the bulk of the way that you take a percentage. We're just not going to multiply by 100 to get a percentage. And I think somebody asked, can you use a percentage? And whew, I don't know what they would do. I guess maybe I could ask. My first advice would be don't. So the CO is 0.55 molarity out of the total molarity, or to illustrate something that comes up in other parts of the whole thing, these are all divided by the same liters. So no matter what the liters is, since they're the same, we can use these as the mole ratios. This is 0.55 to 0.3 to 0.2 in the moles also. So that's why they just borrowed these numbers and called them moles. And then we take the part that is CO over the total. The total, of course, is them added up. And on these, you get a calculator. So we just divide. Oh, and I was also saying 0.34. Remember, these are not official answers. These are just these two teachers who made this workbook. I am very suspicious of just an unlabeled number. I would put that. That's CO mole ratio. Yeah. Well, maybe they get away with it because the XO. I don't know. I don't remember this notation, but if maybe you could get away with it if you put mole ratio CO equals and then equals that, because technically there are no units, and as Chris pointed out, the units cancel out. So it's just a raw number. And I said, well, don't have unlabeled numbers. I realize now that if you put something that means CO mole ratio here, it's not unlabeled technically, which honestly I didn't notice yesterday. We were winding this up real fast. Plus, I could be wrong, but I don't quite know what XCO is. I guess this ratio. They might like it. I don't know. They might like it, let you get away with that. I think this nails it down, and there's no denying it. Then they want KC. Oh, right, because we have molarities, not pressures. So there's no converting between KP and KC. You take the molarity, and yes, water is a gas here. So water does have a molarity. So molarity, using molarities, products over reactants to the power of the number in front, except all the coefficients are 1. So that kind of almost drops out, and we just get the numbers.
Mr. Sweeney.
Yep.
These only work for gases, aqueous, and liquid, right?
K's, you say?
This style of solving equilibrium.
This style. What's style?
I mean, like, you can't find the molarity of a solid. But
You
is that
can't
it?
you can't find the molarity of a liquid either.
Okay.
That's why I was double checking that water has a molarity, because I'm so used to water dropping out of K expressions. Because further on down the line, everything's dissolved in water so often that the water is irrelevant, because the water isn't dissolved in water and it doesn't have a molarity. But if it's going to be a gas, okay, it can have a molarity.
And what about powders? Like, it's a solid, but it's a powder.
They don't mention that it's a powder. We do something called KSP for solubility of product, but the math is all the same again. It's just that you're judging how much of this will dissolve. But the reality is that you can only dissolve so much of a mineral, like a mineral salt, like aluminum chloride, or just to pick something, right? You can only dissolve so much, no matter how powdered it is. So the fact that it's powdered is irrelevant.
All right, thank you.
Okay. Because when I was talking about burning it, that's different. Because water can only accept a certain concentration of a mineral salt. It's not even the water. It's not the water exact. It's not that the water accepts. It's that if you have a solid that's AB and you want to dissolve it, you get A plus and then B minus, and then they are aqueous because they dissolved. Okay, sure. This thing must have some stability and attraction, some stability as a solid and attraction to be a solid. Otherwise, it would never have been a solid. So this is a very relevant and very, very possible setup where this is a solid. So can you get some of it to dissolve? Yeah. And we get into the idea that in a certain sense, anything dissolves a little bit. Of course, sometimes it's extremely small, but so it'll dissolve a little bit, but also you get these things bumping into each other enough, and you then the odds go up that some of it will go backward and make a solid. And so whether you end up making a solid depends on the concentration of the aqueous ions, and not whether this was a powder in the first place.
And in order for you to split this, you just put it in water?
Yeah, put it in water and give it a stir. Now, the extent to which some kid's going to jump in and say, but that can change because I know that when I heat the tea, I can dissolve more sugar. And so forth, right? Sure. Okay. First of all, sugar doesn't split into ions, but yes, it's also true that solids, boy, it might be universally. I can't think of an exception. They dissolve better in hot water. So when we talk about these, we're talking about at a certain temperature. And then you can get a KSP, which is solubility product, but that is only good. Oops, that's not. That's supposed to be at temperature blah. KSP only is good at temperature of whatever Kelvin. Or Celsius. At that point, there's no exact reason not to use Celsius. Kelvin is demanded when you need to do ratios with temperature. If you do a ratio with Celsius, it doesn't work because 10 Celsius looks like double of 5 Celsius. But it's not even remotely double the energy. And so if you do ratios in Celsius, you get cuckoo pants answers. And we did this and then determine KP in terms of KC. No, I won't because it's not on the test, so I refuse. The system is cooled down to a lower temperature. 30% of the CO is converted back. Okay. So here's an icebox. What do we know? We know we started at these molarities. They handed us the change. 30% will be converted back when you reach this new temperature. Okay, what's 30%? Well, so this times 0.3 is this. To be extra picky, 2 zeros, I guess. And that is lost. Therefore, you end up here. And then a concept that comes up about 1,000 times is the ratio between the chemicals. If you lose one of these, you got to use one of those. And you create one of these and one of those. So if you lose 5, you use 5, you create 5, and you create 5. Or if you end up with 0.165 all the way across, except we lose these because we know it's running left because we just said this amount went down. Well, how did it go down? Well, the whole thing went left. In fact, they say it's converted back. So we lose equal amounts here, and then we, in this case, because there's not a 2 or a 3 in it here, we gain the equal amounts of these. And then, therefore, the equilibrium amounts are these once we subtract and add. And then K is the amounts at equilibrium. K is only good at equilibrium. K not, and in case somebody needs to write this down, K is only usable at equilibrium. The whole point is that it's only true at equilibrium. The reaction has a certain overall ratio that it will settle down to by the nature of the stickiness of these things to each other, or the reactivity between these or between these. And so it settles down into into ratios that always give this number, but that's only the number it settles down to. You could put in any amounts at the beginning, right? Some weird numbers like these, and then K will not be true. Not at that moment. You have to give it time to settle down to an equilibrium. So we put in these values, products over reactants to the power of the number in front, and all the exponents are 1, and calculator. Boom. Something on D? Well, E, in a different experiment, 0.5 of H2 moles and 0.5 of CO2 in a 3 liter container. There we go. So what do we want? Calculate the equilibrium concentration. So what's the concentration of CO? So what we're looking for is this box here, the equilibrium amount of carbon monoxide. So we're not at equilibrium. They just put in some numbers. It's extremely unlikely that those are the numbers that produce equilibrium. So let's assume they're not. In fact, they would kind of have to tell you because it would be so weird that they just put it in at equilibrium. They would have to say at equilibrium it is found that kind of thing, because otherwise you wouldn't know. So this is not at equilibrium. So the initial amounts are what they, let's see here. Oh, right, 0.17 because 0.5 divided by 3. So remember, you had to use the molarities. Molarity and not moles. So we started with 0.5 over 3, 0.5 over 3. We have none of this and none of that. The reaction can only go to the right because we only have reactants. So we will be losing these and gaining those. The coefficients are 1, 1, 1, 1. So we will lose some amount of this. So we'll lose an X amount. We'll lose the same amount of X because when you use one of these, you also use one of those. And when you use one of these, you get one of those, and you get one of those. So whatever X turns out to be, it's the same amount. We'll lose a certain amount of this, the same amount of that, gain the same amount of that, and gain the same amount of that. So at equilibrium, we'll subtract, right, and add. We will have these amounts. And we haven't done a lot of that. So is that working? Can I get a yes or no out of both of you?
Yeah.
Yes.
Okay. So K will be these amounts, products over reactants, the power of the number in front, but all the exponents again are 1 because we're starting off kind of easy. And so we will have X times X on the top and this times that on the bottom. And again, we have the loophole where we don't just cross out minus X, we can square root both sides, which means we square root the numerator and the denominator, and because we have perfect squares, top and bottom. So we can just cross out this. Square root of X squared is X. Square root of this squared is that. And do it to both sides equals square root of 5. So we have, I jumped ahead here. So we take this times square root of 5. This times square root of 5. And so X equals square root of 5 times that, and square root of 5 times minus X. What?
Could you rewrite that equation in square form? You know, where it has like X squared and 0.17 minus X squared.
Yeah. You mean you want to?
Only because I feel like it would be much clearer if you wrote it like that.
X squared over 0.17 minus X squared?
Yeah, thank you.
I mean, sure. In which case you can just do this. Dink, dink, ba-bump, like that?
Yeah.
It's the same thing, yeah. Sure. And then again, square root of 5 times this gives me that without X. Square root of 5 times this, of course, gives me square root of 5X. Add this over and then divide. Add this over here. We get new X divide and we get X. Oh, we only have 2 significant figures. So that's here. 2 sig figs.
For the test,
they kind of violated their own. Like I say, this workbook is full of just little things like that. They violated the sig figs by putting in 3 here. What?
For the test, you said use 3 because
if in doubt, if in doubt, yeah.
Okay.
I just mean if in doubt, if you're like, I'm in a hurry and I can't be bothered, or I'm worried I misread this. That's really what I mean. But to be technical, they're wrong. It's 2 because the original data is in 2, right? All of it. And plus, it doesn't even matter if all of it is in 2 because it's the least the least number of sig figs in the original data that constrains the answer. Or I have learned that kids don't know the word constrain. Some anyway. It limits the size of the answer. So if this is in 2 and this is in 3 and this is in 3, you still only get 2 sig figs in your answer. So there's another thing I can go in and change, I guess, make that be 0.12. Oh, also, I got 0.117 and they got 0.115 because of a rounding thing in the middle. I don't remember if I rounded and they didn't or whatever. Anyway, once you go to 2 sig figs, we get the same thing. And they're not going to argue about the difference between 0.115 and 0.117 anyway. It's a reasonable answer using all the correct logic. So I'm imagining that this here is a 2-point problem. 1 point for setting up the correct expression and 1 point for solving it. Maybe. And I think you get both points. Even if you just leave it like this. Because you're within 1 sig fig of the correct sig figs, and this is not stupid different from that. And in fact, I don't even remember who's more correct. I don't feel like rerunning the whole calculation. Something to repeat on E? Because that's 3.1, isn't it? In general?
Yeah, I believe so.
Well, I don't mind. Like I said, my frustration comes from kids not admitting that there's trouble, so I can just address it now. Anything else on 3.1? Anybody?
This is like an issue I have about all 3.1. When do you know to
All
use
of
the
it.
table?
Use the table?
Yeah. Or when do you know it's that type problem?
When you need to, I would say when you need to achieve equilibrium, but numbers, but you don't have them. If you only have initial, but you need to calculate k, or you have k, right? And what we haven't done yet. Oh no, excuse me. You know what? I want to make another point. I realize I kind of dropped the ball a tiny bit here. In fact, here, to be picky, I did not answer the question. I solved for x, and you know what? If you leave it as this, I'm telling you, I think you missed the point. They did not ask for x. They asked for the molarity of carbon monoxide, and if you don't at least write then equals CO brackets or molarity or capital M CO, right? I'm not saying you have to use a different line. I'm saying you have to note it. So this is an incomplete answer. It turns out that X is the value of CO at equilibrium. But what if it wasn't? What if you needed to double it or add it to something? And so, actually, I thought of that, Chris, because I was saying if you have initial amounts and then maybe you need to calculate K, like this one, right?
Yeah.
Or what if you have K, because where is equilibrium
I think that came
It's
from
at the top.
a prior part. Yeah, part B.
You know, I read through these so fast, and I've seen them so off. You know, right now. So where did we get that k equals 5?
I think it was part B.
Oh, yes. We calculated that it's 5 back in part B. So now that we know k, and they at 2000k, did they say that it's at 2000k back up here?
Yeah, it's in like the prompt part before part A.
Oh, yes, they say it's at 2000k. Okay. They're pretty good about that. That if you read through everything, you can say, oh, yes, this is the same thing. So when I solve for kc here, I can use it here because it's the same reaction at the same temperature. So when do you need equilibrium? Well, when you're asked for k, or you need to solve for something at equilibrium, right? So I'm saying the icebox gets me from initial amounts to equilibrium amounts. So when you have to change from initial to equilibrium.
Thank you. That actually really helped.
Oh, good. Okay. Something else on 3.1?
Will they mark us off on the real test for not using the icebox?
No, I think that came up. No, the icebox is just a good tool. What they do need to see is an actual, calculation setup. And some kind, I can try to remember to ask somebody, but I think that I was told in the seminar in San Diego that if you can show just some kind of concept that this minus that is that, it's not the box. It's, do you seem to know how you got there? And then show, you could put this squared, of course, and but what they're trying to guard against is just peeking at your neighbor real quick because the proctor looked at the clock, right, and writing equals 0.87. You have to show that it looks like you know what you're doing. Is basically what they said. It's not the box. That's the point.
Okay.
Well, oh, look, KSP 3.2, I suppose. So you should have printouts. I gave them. Well, soluble salts dissociate 100% into ions. And here is the point. Insoluble salts, well, they're insoluble. They don't dissolve at all. Well, yes, say that. But they dissociate, or that means come apart. And so we mean both come apart and by that we mean dissolve. Because why else are they coming apart? If you leave table salt in the shaker, it doesn't dissociate. It only dissociates when you put it in water. Or melt it. You're not going to be melting it. Ionic compounds have very high melting points. And there's nothing to calculate about them. It's kind of uninteresting. You melt them and you get melted salt. That's it. There's no math to figure. If you have 100 moles of table salt, then you have 100 moles of Na and 100 moles of Cl. And when you melt it, you have the same thing. There's just the same amounts. They're just all running around in liquid form. So that's all there is to say. There's nothing interesting. So the maximum amount an insoluble salt associates its solubility. So this is the rating of how much it will dissolve. Maybe note to self. And then if you look at solubility tables on the internet, they're often written for industry. And I understand that this is more useful because if you're trying to dump bags of stuff into vats to make, get stuff done today, calculating the molarity is kind of pointless, honestly, because there's no such thing as a molarity scale. So what you want to do is rate it in pounds or grams. And so how much can we dissolve? Well, if we have this many kilograms of water, we can dissolve this many kilograms of salt. Is very useful. However, in designing a system and working with how much this stuff will dissolve, it only works in molarity. It works in the number of ions and not the grams of the ions. So when you're, about to dump a barrel full of stuff into a vat, sure, grams are very useful. But if you want to design the system, figure out, wait a minute, how much does this stuff dissolve? And then when will the solid appear? Grams are useless because different salts weigh different amounts for every mole. The molar masses are different. And it's the number of ions that rules the solubility, that controls whether this stuff will dissolve and how much, depending on, and then it depends on the exact salt. So the molar solubility would be the solubility rated in molarity. So here's our standard sort of generic solubility or dissolving reaction. We have A and X. Why not A and B? Because it's just stand-ins. So when you dissolve something, and if they have one of these and one of those, they come apart and they become A positive aqueous and X minus aqueous. And so K is products over reactants to the power of the number front, with a very special note that the reactants here don't count mathematically because the reactant is a solid and doesn't have a concentration. Run that through the brain a couple times.
So the KSP thing is like products over reactants, but there's no reactants, so just products.
Yeah.
Okay.
Repeats on that. So, example 1. So we have the molar solubility. So this is not K. It's how much can dissolve. Hold on. Right. Okay. Yes, it is. So in fact, find KSP, right? So this is that rewritten in non-scientific notation. And for some reason that I never figured out, I guess it's just solubility. A lot of these people like to use S instead of X when they're dealing with these solubility expressions. Sure. Doesn't matter, obviously. It's just a stand-in variable. But the point with silver sulfate is you're supposed to recognize that there are 2 silvers and 1 overall grouping of sulfate ion. And they expect you to know this without having to tell you. So this is part of the answer, so to speak, in case you want an extremely thorough setup, which, again, discussing that icebox thing, you don't have to actually write out. But if they say silver sulfate, also they would give you the formula, though. To be honest, they would tell you that silver sulfate is Ag2SO4 because they don't consider this test an ion memorizing test, and they don't want kids getting confused and thinking it's SO5 or something. You know what else? I don't remember if they would mark you down for the charges being wrong in case you don't get an ion chart. Huh.
Mr. Swaney,
Yeah.
if they give you like silver sulfate, then you can tell that there's 2 silvers and 1
Yeah.
sulfate. So you can tell that the ratio between them at least is that the
Right.
sulfate is twice as negative as whatever the silver is.
Right. Right. But is it 2 and 4? Plus 2 and minus 4? I don't know. They probably wouldn't mark you down for the charges being off because it's not really entirely the point. I could try to remember to ask. So they do expect you to be able to write this, though. We're going to get 2 of these and 1 of those. At the moment this drops in, we, of course, have 0 amount. The molarities are 0. Then they climb. And if you want to use X or Q or P, they can't complain. But we're going to get 2 of these and 1 of those. So this is going to be double whatever that is. The unknown amounts are going this is going to be double the unknown amount of whatever that unknown amount is. And since we're adding them to 0, they just become this, which is so typical that honestly, I stopped writing the icebox for a lot of these. They say, they write some problem where you realize, oh, the starting ion amounts are 0. I stopped writing the box. You're just going to add this to 0. Like, do I really need to write that? This whole box? But they're being very thorough to show us what's happening right now. So what will K be? What will K turn out to have a value of? And right, okay. This is molarity of the salt that can be achieved. Or molarity of the salt maximum. How about that? So what you can do is say, sorry, hiccuping here, the overall molarity. But remember that if we have A to B, which is what we've got here, right? If I dissolve 3 moles, 3 moles goes into solution. 3 moles dissolves. How many moles of A and how many moles of B do I have?
You have 3 moles of B, and I want to say 6 moles of A.
Yeah, exactly. If you have 10 of these, don't you end up with 20 of this and 10 of that? And when I do red Legos to blue Legos, and I say you have 10 red blue Legos like this, if you break it up all apart, don't you have 20 reds and 10 blues? So when I break up 3 moles of this, I get 3 of the B and 6 of the A. Jadalyn, does that work? She stepped away. No? Yes? No? Yes? Okay. So this is the amount that dissolves, but this number will be double whatever they just said. This number, because it's 1 here, will be equal to what they just said. This number is the S. It's the fundamental number. One of these will get you one of those. And we called it S. So this number is S.
Wait.
Hmm?
Yeah, I had a question on this here. It doesn't really make too much sense. Why are they using 2.3? Or 2.29 times 10 in the negative second.
Why are they using 2.3? Where?
Why are they using the molar solubility number? And plugging in for S.
That's just what I was trying to explain.
I know, but
Yeah.
it didn't really make sense.
Okay. So if I call this is my grouping of Legos, right? So 10 sets gets me how many reds and how many blues?
20 reds, 10 blues.
20 reds, 10 blues. So this is the molar solubility. This is the amount that I'm going to break up. How about this? 10 sets broken, right? Broken up.
Wait. Why would that number be a molar solubility?
Because I'm telling you how many of these, moles is how many, right? How many of
Yes.
these can dissolve? How many of these you're going to break up? Because when they dissolve, they break up, right?
Oh, yeah.
How many of these will water let us break up at this temperature? Or per liter anyway, right? If you have exactly 1 liter of water, how many of these at this temperature can you break up just by, stirring a lot? And the answer is this many per mole. Per liter, This many per liter, right?
Right.
But of course, changing the temperature is cheating. I mean, and really cheating. I know I throw that word around, but genuinely it's cheating because the K value and the molar solubility value will change if you change the temperature.
Yeah.
So throw a bunch of this in a liter of water, stir it for 10 minutes, and this is the number rated in moles of these that will break up and dissolve.
All right, that makes sense now.
And you can call it, Qbert, but anyway, it's, you can put any. Does anybody know what Qbert was?
Yeah, it's like a
Duh.
pyramid thing.
What?
They're on a pyramid, right? And they jump from square
Oh
to
yeah,
square.
you're right. It's an old video game that I played about once. It didn't look that interesting. The really weird thing was that because it was a two-dimensional representation of a pyramid with all these blocks, you could get the whole pyramid to turn inside out in your mind if you stared at it just right. And then Qbert was jumping on the bottoms of the blocks. Because it didn't have shading, because it was such an old video game that it was all vector graphics and everything was just lines. So they didn't have the ability to shade. Okay, anyway, dumb stories from the 80s. I can break up, let's say I can break, if you stir it, you can break up 5 of these. Okay, if you break up 5 of these, don't you get 5 of that? One of these will get you one of those. But if you get 5 of these, you get 10 of that. The point being that this number will be double whatever you just said for this, and this number is equal to whatever, because there's a 1 here and a 1 here, this number will be equal to whatever you just said is breaking up out of here. Pause for all the kids listening to the video later. So what is that? Well, I don't know yet. Actually, excuse me. I do know what it is. I take that back. I know it's 2 times that and 1 times that, right? K, though, is products over reactions, the power of the number in front. And the extra trick here is that then the 2 gets used twice, because this value is double whatever that is. And then as an independent concept, this value will be taken to the power of the number in front. So ignore the exponent. Do we agree that this number is double that number?
Yes.
Okay, now Forget this 2. This value will be squared because the number in front is squared.
Yeah.
So you don't get to say, people listening later, what do you mean you use the 2 twice? They're independent ideas. This number will be double whatever that is. And then just say there's value A and value B, and value A will get squared, and value B will be to the first power. Which means that since there's a whole lot of 2-to-1 ratio in these things, you get a lot of 4s cubed. In fact, we get to the point where in other years where I've just said, oh, look, it's a 2-to-1. And for the 20th time, 4s cubed. And like, I didn't draw the box. In fact, I didn't even write out this. We've just seen it so many times. And then you get a calculator on these because how else are you going to do it? So take this number, cube it, and multiply it by 4. And that is K.
What if you use less, like in the initial, for the amount of stuff you're dissolving in water? If it's less than the molar solubility,
That is the
is
next
mass still
question.
the same?
Well, again, right. That actually comes up, and I think that's the next question right here. This is the max, right? Note, I think I even said max, right?
Yeah.
So max, right? This is the max that you can dissolve. You can stir 10 minutes or probably stir an hour and get no difference. Probably, I'm assuming after 10 minutes that you're done. And stirring another second won't help. So let's pretend that I'm right. Stirring it an hour won't get you any more. It's not possible. I mean, as I said before, this stuff has some attraction to it between the ions. Otherwise, why was it ever a solid, right? So because it's an insoluble salt, by which we mean it's only slightly soluble, just a little bit. If you get these things so concentrated in water, well, they're kind of sticky to each other, metaphorically. Some of them will start to stick. And if you try to get them past their maximum concentration, so many stick together that it equals the rate of the ones dissolving. And you have an equilibrium. You can't violate this number high. This is the max you can dissolve in 1 liter at this temperature. But you could dissolve less. What does this reaction mixture look like when 0.01 moles is in a 1 liter solution? Well, what's the max moles you can get in 1 liter? 0.0229, right? Per 1 liter?
Yeah.
So if you try to achieve 0.01, if you dump in 0.01 moles in 1 liter, what happens? Well, you don't achieve the max. It all dissolves, right? I mean, you might have to stir it a while or whatever, but. Okay, I said 10 minutes. We'll pretend 10 minutes, whatever the time is, right? You put it in a beaker with an automatic stirrer, and yes, those exist. And give it half an hour, and I bet it's all gone. Because this molarity does not achieve that, and this is the max. Can you achieve less? Sure, why not? I mean, honestly, it's like saying my max high jump is 6 feet. Can you jump 5? Dude, I just told you I can do 6.
And then so the next part would be if you have too much, you wouldn't be able to dissolve all of it. Or like the analogy you just used, if I could jump 6 feet and you asked me to jump 7, I can't do it.
Right.
All right.
So what does it look like when 0.04, which I'll point out is decidedly greater than that, it's almost double, is in a 1 liter solution? Well, first of all, I don't know how they ever got, when they say, I don't even like this answer. I think I want to change this one now. Because we said at this temperature, whatever temperature this is, right? Oh, by the way, there's a standard temperature, and I think it's 25 degrees Celsius water. So if they don't say what they're doing, it's just assumed it's at 25 degrees Celsius, but that won't even matter. They in the real test nowadays, they would probably say, you know, the molar solubility at 20. Oh, look, they did. It's just I blew past it because they're not going to change the temperature on you. So I don't even frankly care what temperature it was. The max is this, great. Ba 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 ba. The K for whatever temperature they said that I didn't read is this. But by the way, the standard temperature for these things is 25 degrees Celsius. Although I'm not sure that will ever come up. Here's my point. At 25 degrees Celsius, how did they get 0.04 moles to dissolve in 1 liter? Well, the answer is they didn't. So if we're only talking about using just this, this number is not possible. Not in 1 liter. However, there are problems later on that we get to where through various other means, it turns out you have produced ions that are equivalent to this. So how about well, at the moment, let's just say this. If you manage to have this many moles in 1 liter, what would happen? And what I want to say is this will dissolve if you give it time and stirring, and the rest will not dissolve. How about this? This amount, this is the excess, this is the difference, will not dissolve, is what I want to say at the moment. If you have this much powder of this, and you stir it and stir it and stir it, the maximum molar solubility, the molar solubility will dissolve, and the rest of it won't. Is Jadlyn back?
I'm here.
Oh, did you step away for a moment?
No.
Oh, because I asked you for something at some point and you didn't respond. Okay, well, just double checking because Chris has been talking, so I'm paying attention to you. Is there something I should go back to on this?
No, I understand.
Okay. So example 2, the KSP for blah, blah. And again, they would give you the formula. Oh yeah, especially in this case, that's really dirty pool to, where did that phrase come from? Billiards, I assume, but there is a super weird thing about mercury that if you have mercury charge +1, it occurs in pairs. That's how they got this, by the way. Each atom is +1, but for reasons that was never explained to me, mercury as a +1 pairs up and does not occur in singles. So since it occurs in pairs, it overall is +2 and you need 2 Cl minuses. So they would extra triple reasons have to tell you the formula. But they would. And they probably wouldn't throw mercury at you for crying out loud. These guys are playing to be difficult here. So the KSP is this. Calculate the concentrations of the products. Because look, they went, yeah. Did I fix that on yours? Does it say that?
It still says calculate the solubility.
Okay, I need to change that because look what they did. They calculated the concentrations of the products. So the question is bad. So what was I going to change? This and this. And then like put in the formulas. Maybe this year I'll dial in this thing a lot more. Okay. So we need this, we need the concentrations. So we at you know what we need? Concentrations of the products at equilibrium. That needs to be stated. Of course, I don't know how else I could calculate it, but to be picky, that needs to be stated. So K is only good at equilibrium, right? That's what I'm saying. I can calculate it at equilibrium because I know K, but if it's not at equilibrium, I can't use K and I'm stuck. So we need to say the concentration's at equilibrium. So how much product did we start off with? And the answer is 0 because I didn't have any of it dissolved at the beginning, presumably. And then this will break up only into one unit here, which is the extra picky point of this, which is why they wouldn't ask this salt. But anyway, and by the way, plus minus pairs are salt, plus minus groupings are salt, even if you could never eat them. This is presumably hugely a giant no-no. It's got mercury in it. Don't eat that. But it's a salt technically. So this salt will give you one of these and two of those. So one of these will give you one of these and two of those. So when we break up one, you'll get one and then you'll get two. So this number is double whatever that number is. What is that number? Well, you know what? We don't know. We don't have the molar solubility, do we? So what's S? I don't know. But we can proceed because if we'll combine everything, it turns out we only have one unknown. So remember when I said two of these and one of those comes up over and over again? This is double that. And then, as an independent idea, it is then squared. So we get 2s squared times s to the first. And I'm pausing so everybody runs that through their brain because that's an important point. Which is then equal to the value of K. This is 4s cubed equals that number. Divide by 4 and then cube root, and we get S. And you know what? Hey, kids watching this later, I'm going to go hit pause and actually do this and see if we get that. And I'm going to hit pause on the recording. So everybody here got that number, and that is the value of S. This is a very tempting place to stop, and that is not the place to stop. That was not the question. This is the molar solubility, but they didn't ask us. I realized that says solubility. What they went on and did is not that. And I'm changing that question because we already, and this is more interesting anyway. So if the question is the concentrations of the products, the concentration of Hg2, 2 plus, is equal to S, but Cl minus is equal to double S. So for, I know, like the 10th time, but answer the question. And it's really tempting to not fully answer the question. And I've done it in front of 10 kids, and there's X. And some kid says, that's not the full answer. Oh, whoops, here, have a starburst. So rank these in order of increasing solubility. Maybe you heard me say, bigger is less negative. And it's one of my favorite phrases because it comes up so often. And also, it even made Mrs. Nagin say, "Ooh, I'm going to use that." And I thought, "Oh my gosh, I helped out the math department." Bigger is less negative. Bigger is less negative. If you have salt AB and salt CD, and then this K equals 2 and this K equals 1, then somehow that looks like 0.2. I don't know what happened there. Anyway, okay, 0.2 and 0.1, then this dissolves better. However, Chris is right and they are right. The real solubility is based on the S value. So what we have to do is solve for S, because S stands for, in one way of speaking, the amount that this can dissolve. Remember, I said the molar solubility is the max that can dissolve of the solid. So what we'll do is take the KSP and then put it equal to the expression with S in it. We're going to get one of these and three of those. So when I dissolve S number of the whole thing, I'll get S of that, of the cobalt, and I'll get 3S of the OH minus. And then it is again cubed, which is 27S to the fourth. And then to solve for S, I take this divided by 27 and then the fourth root. Also, I will point out that the fourth root is the same thing as taking something to the 1/4 power. So we solve for S, and S is this. This is the maximum number of moles of this salt that can dissolve per liter of water at this temperature. This will be 3 of those and 2 of those. 3 of this and 2 of those. And then this will be to the third power, and because we'll have 3 of them. And this will be to the second power because I have 2 of them. So we get this, which is well beyond the scope of the numbers they use in the test. They probably don't even use this. But I mean, they could. I don't honestly, I don't see a problem with them using it. If they use these, I'd be like, well, kids have got to be able to do that. I mean, conceptually, it's the same thing. It's just a different number. Divide by 108 and take the fifth root, which is to the 1/5 power, and you get S. We're going to get one of these and one of those. So they are equal. They are both S. They are then both to the first power. So we get S squared. So solving for S takes the square root of this. This actually is a good exercise. And all I need is honest answers, because this kind of stuff comes up. And we need to be able to manipulate this and then visualize. I'm going to get one of these. It'll be then to the first power. I'm going to get 3 of these, but then it will also be to the third power. And it's okay to say, no, I need you to write that out further. It really is. Chris, is this working for you so far?
Yeah.
Jalen, does that work for you? Or do you want me to write out one of these fully all the way through?
Can you write it out?
So CaOH3. CaOH3 would be that. So I will get one of these and 3 of those when one of these dissolves. Does that work?
Mr. Sweeney.
Yes.
Okay, what?
It's cobalt.
Oh, it's cobalt.
Yeah.
All right. So I will get one of these and 3 of those. So this, if I call dissolving one of these as S, then I will get 1S, and then I will get 3S. Does that work?
Yes.
And then when we're doing equals K though, or KSP in this case, it doesn't super matter. This is the concentration, but the concentration is taken here. Let me do this. 1 CO plus 3 plus 3 OH minuses, right? So these are the concentrations because when I dissolve one of these, I will get one of those and 3 of those. But the concentrations are taken to the power of the number in front. So I will get S to the 1 times the concentration is 3S, but then it is also taken to the third power. That.
Okay, I understand.
Okay, so that's how we arrived at that. And when we just solve for S, Chris is right. You cannot just stare at K. I'm so used to, it seems like you can do it in other cases. Anyway, so these are the molar solubilities. And then we can say bigger is less negative. So this is the smallest. So this has got to be number 3. Or smaller is more negative, right? Minus 13. These have the same negative exponent. And so this is smaller than, this is smaller than that. So it's 1, 2, 3. We can predict whether a precipitate will form. A precipitate is a solid, not dissolved. That's the huge point.
Is the precipitate just, is it the separate ions still, or do they recombine?
No, they very much recombine. That's basically the entire point. Good point. I'm glad you asked that. The solid will be back together. That is the whole point. You are right. So what we can do is say, so you have so many ions in solution. Does that exceed the molar solubility though for the salt we're talking about? Because if you manage here, again, I don't want to mark up this paper. If you can, what is it? Calcium and phosphate? Calcium, what are we going to talk about? Calcium.
Chloride.
Calcium, silver chloride.
Oh.
Right. And also they got these swapped apparently.
Yeah, isn't it silver nitrate and calcium chloride?
But anything with nitrate cannot precipitate because nitrate's a super soluble. So when we talk about what will precipitate, it can't be anything with nitrate.
So wait, why do you use silver and chloride? Because calcium's also super soluble? Or?
No, it's not super soluble. Because it's the only one I have KSP for. Honestly, but in this problem, I can't answer the question if okay, I do have a reason. Okay, you know what? You want to do that first? Okay, what do we have? Calcium chloride and silver nitrate, right? Okay, calcium chloride and silver nitrate. They are currently both dissolved, though, when they are delivered. They have these concentrations, right? It's a solution. It's dissolved. The word solution means it's dissolved. So have we exceeded the molar solubility of calcium chloride? No, you can't exceed the molar solubility. But is this in a state where it is okay with being dissolved? Clearly, it was delivered as dissolved, right?
Yeah.
Okay, is it going to precipitate? If it was going to precipitate, it would have already done it. It's okay with the state it's in. So what are our possibilities? Calcium chloride, it's already dissolved. Is it going to precipitate? No. Silver nitrate, it was delivered, dissolved. Plus, nitrate is a super soluble, so unless you go absolutely bananas, it's not going to precipitate. Is that a possibility? No. So swap the pairs. You could do silver nitrate. I just said nitrate can't precipitate, so that's not a possibility. What's the only possibility? Oh, it's that. But anyway, the only possibility of precipitation is silver chloride.
That makes sense.
Okay. So we have a certain molarity and a certain amount, and a certain molarity and a certain amount. Will a precipitate form? Oh, also, I see here a couple years ago I crossed these out. Did I fix that? Does the line with 5.0 E negative 6 correspond to chloride?
No.
Still not? Okay, I need to fix that also.
Well, I think. Oh yeah, never mind. Yeah, they're wrong.
Okay. Hey, everybody, let's go back and change these because the numbers what corresponds to 8.0 E negative 6 is the one with the chloride ion in it, huh? Yes, I am right. They were wrong. These are switched. So what we need to do, though, is find the new molarities once they are added together. So in another move that comes up all the time, molarity times liters equals moles or moles per liter times liters cancels out the liters and gives you moles. Yeah?
Yeah.
So if I take the molarity they gave me and the liters, you could put 0.5 liters, whatever, right? That would give me the moles that was delivered. But the new molarity will be the moles divided by the new liters formed when I pour these together. So we have to take the moles delivered divided by the new amount of liters to get the molarity. And because we're going to multiply by volume and divide by volume as units, it doesn't matter if you use milliliters. Because if you do liters, you just get 0.5 over 0.8, and it's the same ratio, and you get the same answer, so no one really cares. And then we do the same thing. So this is the molarity of Cl minus delivered, newly created. This is the molarity of the Ag plus newly created. Oh yeah, look, here's my taking the reaction, right? And here's the two other possibilities. Actually, there's me explaining it before. This isn't going to be anything precipitated. Oh, this has got to be the precipitate, huh?
Yes.
So, will we get a precipitate? Well, we now have molarities of the component ions of AgCl, which is the only possible solid to create. Excuse me. Well, is that greater or lesser than the molar solubility? Well, if you do a Q on this, do you exceed K? So if we take this to the first power, because there's going to be one of them, right? times this amount to the first power because there's one of them. So here's the AG plus. Here's the CL minus, and of course it doesn't matter which one goes first. We get Q. Remember, this is Q.
Mr. Snurry,
Yes.
they say Q is greater than K.
Right. Isn't it?
Oops. I thought K was 8 times 10 to the negative 6. That was my fault.
Oh, yeah. The KSP is this, right?
Yeah.
Okay. So exactly. Okay. You do know where we're going. You just read the wrong number. Yeah. Okay. So I was just about to say, literally, like the next sentence was going to be molarities that form a calculation, a K calculation that with a value that is greater than K are not possible. That's the point of K. In a sense, it can't be done. If you just delivered molarities that generate a K value bigger than actual K, you violated nature. Well, in a sense, what will happen is nature will then take this reaction of, I guess did they not run it, actually write it out. We will have, here, they will take this reaction, nature will take this reaction and push it left. If the values of these are high enough that the K math delivers a number bigger than the actual K, nature will push it left. Or, to say it another way, these have a stickiness such that if you try to violate K, you can't do it because these get close enough together. There's so many of them in such proximity to each other that they start actually sticking and making solids. Some of them, anyway. And that will continue until these molarities drop to such a point where K is true again. K is actually achieved, that K is the number that you would get using the molarities at the end of this. These will drop, nature will drop these molarities until such a point where they generate a K SP that is actually equal to that. How does it do that? It runs this reaction left and creates solid or a precipitate. Well, precipitate is probably the noun form. So yes, a precipitate forms.